All right, we're continuing our work in Unit 6. We're now on Lesson 5, and we're going to be looking at vectors in R2 and R3. So previously we had described vectors geometrically by giving them, as we can see in this picture, we gave them a direction via an angle using either quadrant bearings or bearings. In this particular case, we could say north 45 degrees to the east, or east 45 degrees toward the west, or the north, sorry. And we would also need a magnitude 3 times the square root of 2. So this one would be a geometric vector. Now we're going to be looking at R2 and R3, which would be the Cartesian plane. R2 and R3 would be, not sure what the equivalent of prism, like the equivalent of a plane in R3 would be a rectangular prism. So R3 is going to be a rectangular prism. So what I want you to think about now is why the vector that has its tail at the origin and its tip at 3, 0, which I could write as, 3, 3. Its tip is at 3, 3. So I'm going to call that vector OA 3, 3. I want you to explain why this vector is the exact same as this vector. Now, in order to prove that there's the same vector, what you're going to need to do is find the magnitude of this vector. That should not be too hard because we know how to use or find the magnitude of that using the Pythagorean theorem. So that's step 1. Again, you can be in control of the timing. So the length of this side here is going to be 3. The length of that side there is also 3. So we should have the square root of 3 squared plus 3 squared. 9 plus 9 is 18. That's the square root of 18. This is 9 times 2. So the square root of that 9 is 3 and times 2. So just showing you again where that's come from. That's root 9 times 2. Square root of 9 being 3. So this is 3 root 2. So I've shown they have the same magnitude. Then what I need to do is show that they have the same direction. So what I need to do is calculate this angle. And to find that angle, I'm going to use, again, opposite over adjacent. That's 3 over 3. And then I'm going to need to do the inverse tan of that. So let's see where that takes us. Tan of 3 over 3, the inverse tan of 1 is 45. So I've now shown that this angle is 45, and I've shown they have the same magnitude. So this is representing a vector in geometric form, and this is algebraic form. So let's move forward to the next slide. So thinking about the uniqueness of coordinate vectors. So Descartes' invention of the coordinate grid allowed geometry and algebra to be connected to each other, right? We could see, think of the equation of a line. They were solving linear equations, had no idea what they looked like until Descartes invented his grid. Same with quadratic equations. They were solved, but they had no idea what they looked like. So the key when that was invented is we could now connect geometry and algebra. Now we can extend this use to vectors. We have geometric vectors. Now we're going to look at algebraic vectors. So if we consider vector OP to have its tail at 0, 0 and its tip at some point A, 0, anywhere on the x-axis, P is a directed, I'm going to call it a directed A units away, because we could be A units on this side, which would be positive A, or we could be A units on that side, which would be negative A. It's only going to occupy one position on the axis. That's the key. So negative 4, 0, that tip is unique. There's only one place it can go. 4, 0, that tip is unique. There's only one place it can go. If that's the case, then this vector OP is going to be unique. And that's going to move us forward to the next slide. If we are in R2, which is the xy plane, then P, that's the point AB, is the point that's located A units from 0, 0 along the x-axis, and P units parallel to the y-axis. This position vector OP now, so we're now going to come with algebraic vectors OP. They always have their tail at the origin, and now their tips are going to be at the point A, B. So OP, as I've noted down there, is going to be given this. So now we're going to have to be careful, because you're used to thinking of this as an ordered pair. And if we put this in front of it, that is a point in space at 2, 3. But if what precedes that is the name of a vector, we're now defining a vector that has its tail at the origin. So its tail at the origin, and its tip would be at 2, 3. see if I can draw that effectively. It would be there, and then we would be thinking about that vector there. A is going to be the x component of the vector, and B is the y component of the vector. So this is our algebraic vector. Now that we know the difference between an algebraic and a geometric, we're going to need to be able to convert back and forth between the two of them. So, got a little pen handy. If I give you a geometric form, so that means I'm giving you theta and r, right, which would be the magnitude, and I'm giving you the angle between the vectors, well, not the angle between the vectors, I'm giving you an angle that describes that vector, then to find the x and y coordinate so that we can give algebraic form, the x coordinate is going to be r cos theta, and the y coordinate is going to be r sine theta. And these are just coming from your definitions when you did unit circle stuff. So you had an angle theta, r was the radius from your unit circle, that's y, and that's x. Then you knew that sine of theta would be y over r, and you knew that cos of theta would be x over r. And so in our particular case, what we actually need now are the y and x coordinates for that point. So the y coordinate is going to be r sine theta, the x coordinate is going to be x cos theta. The other way to do it is to use our tangent definition. So tangent of theta is going to be y over x. And because we have a Pythagorean relationship in our unit circle trig definitions, we know that x squared plus y squared is r squared. This one is going to be a bit more work, but walking through an example on the bottom, let's say vector OA has a magnitude of 1.8 and it's on a bearing of 51.9 degrees. Then if I want to know what the x coordinate of this point is, I can just say 1.8 times the cosine of, not sure, let me just pause momentarily. All right, yeah, we're fine. We're on a bearing of 51.9 degrees, which means I'm giving you this angle right here. But the angle that we use in trig is not the angle between the y-axis and the vector or the line. It's got to be this one down here. Put a check mark there. So this angle now is going to be 90 minus 51.9, which gives me 38.1. So we're not doing 1.8 times cosine of 51.9. We have to do 1.8 times cos of 38.1 because I did say a bearing of 51.9, which is the angle between our vector and the y-axis. We need the angle between the vector and the x-axis because that's how our trig functions were defined. So to find y, we could do r times sine of 38.1, giving me 1.11. I think that's nice and quick and easy. If we're going to use a tangent relationship, I'm now going to plug in. So from here I can get y is equal to x tan theta. And then substitute that in there. And now I'll have an equation. All right, a little tickle in my throat there. Oh, we're good now. So then I would plug that into here and I'd get x squared plus x squared tan squared. And then I'd have to factor out an x squared and then, isolate that. More work, but I'll show you what that would look like here. So y equals x times tan of 38.1. As I said, we've got x squared. When we square this, we get tan squared times our x squared. We factor out an x squared, we're going to get 1 plus tan squared of 38.1. And then I would get 1.8 all squared, and that would have to be divided by, again, I'm going to show you, when we factor out x squared, we're going to be left with 1 plus tan squared theta. And whoops. And then what will happen is over here, we're going to have to take r squared, and we're going to have to divide that by 1 plus tan squared. And then when we isolate for x, we'll have to take the square root of all of that, and we're going to get 1.41, which is what we got over here. And then if I want to find y, I'm just going to back substitute that 1.41 into there, and I'm going to multiply that by the tan of theta, which was 38.1, or theta, which was 38.1, and that gives me 1.11. So I would probably reject this method as being too much work. It's more direct just to use this here, which is why I highlighted that in blue. I think that's the easier way to do it. All right, what if we give you algebraic form or Cartesian form, right? Algebraic or Cartesian vectors. So if I give you a Cartesian vector, you have the x and y coordinates, and the best way to find theta and r for the geometric vectors is to use the tan. We know that theta is equal to, now let's just do tan of theta, is equal to y over x. So that means theta is the inverse tan of y over x. And from our Pythagorean relationship, we now know that r is the square root of x squared plus y squared. So working through sort of like the example we did from the previous page, if right now we are at 3, 3, then theta is going to be the inverse tan of 3 over 3, which is 45. And the magnitude is going to be, or our r is going to be the square root of 3 squared plus 3 squared, which is 4.24. And again, I can move this vector somewhere else, and then we can see what's happening. Let's move it up to there. So the inverse tan of 5 over 5 halves is about 68.2. 2 squared plus 5 squared, giving me a magnitude of that. Then I can move this somewhere else, and then my calculations will update. If we're on a bearing of 19.5, then the angle between the x-axis is 70.5. The most direct way to do this is to do r cos theta. All right, so that's an important concept, being able to convert from geometric to algebraic or Cartesian, and also from algebraic or Cartesian back to geometric. All right, so that's 2D done. So these were how we were going to do things in 2 dimensions. Now we're going to extend to 3 dimensions. All right, so in R2, and you're used to R2 being sort of a, I'm going to say a rectangle on your desk facing you if it's a piece of graph paper, or you're used to seeing it on the smart board or a blackboard on a bit of a vertical surface. So no matter how we look at it, they are flat surfaces that extend infinitely in all directions. And any point on that plane can be represented with 2 coordinates, x, y. What we're going to do now is go to R3. And in R3, a point needs 3 coordinates, 1 for each dimension. So points are going to be represented by x, y, z. R2 has 2 axes. It has an x-axis and a y-axis. So R3 is going to have 3 axes, an x, a y, and a z. They will meet at right angles the same way in R2. Our 2 axes meet at right angles. And now the origin is going to be 0, 0, 0, rather than just 0, 0. Many ways we could orient. Now, when you look at the smart board or the blackboard, right? Because this right now you're looking at this is perfect because this is how you would see a blackboard. And on the blackboard, your teacher will label this X, and your teacher is going to label this Y. That's typically how you're used to seeing things look. Lots of ways we could orient when we have this z-axis. It could come right out of the board, or you're looking at this on your laptop now, I imagine. So imagine it coming out perpendicular. Hold a pencil perpendicular to the screen of view. That possibly could be the z-axis, but there's lots of ways they could be oriented. And it turns out the method we're going to be using for orientation is the right-hand system that's shown on the left. And if we think of the YZ plane as the blackboard and the x-axis is coming out. Now students maintain, that they hate this, they don't like this, but I do want to show you that this plane that's sitting right here, maybe I'll show you that, that's the XY plane. It's oriented the way you would normally have paper oriented, because you're used to seeing something on your desk, and I'm going to argue for you that this is what your desk would be. That's the plane for your desk, and you're used to the XY plane being that. When you look up, whoops. All right, not sure where that went to, but when you look up and you're going to see the YZ plane, it's oriented that way. You're used to in class flipping back and forth between the two. When you're looking on your desk, you see your graph paper in this orientation. When you look up to see what the teacher's doing, you see it in that orientation. So now we're moving to 3 dimensions, so I'm just going to hide these. And in 3 dimensions, thinking on how a teacher normally wrote stuff on the blackboard, right? This was X, Y. This is now going to be Y, Z. And coming out, if you're looking on your desk right now, coming out of your paper on your desk, that would be the x-axis. So this is the right-hand rule. There is the XY plane. And again, I'm just pointing out to you, that's how you normally orient your paper anyways. That's the XY plane. The YZ plane is where you would have seen the blackboard before. And the XZ plane is this one right there. So again, I'm going to go through it again. There's the XY plane. There's the XZ plane. And there is the YZ plane. That is the right-hand rule. All right, moving forward to the next slide. So if I was meeting with you face-to-face, what I would do is I would have 8 Kleenex boxes and I would stack them. I would have 4 on, I'd be doing 2 by 2, and then I'd have another section of 2 by 2 on top of that. So I would have 4 Kleenex boxes on the bottom row, and then a row on top of that, another 4 Kleenex boxes. So you are used to, where can I draw this? Let me go back a slide. So let's think about 2D space here. 2D space gets divided into 4 quadrants, quadrant 1, 2, 3, 4. So 3D space is going to be divided into 8 rectangular prisms. So going from a quadrant, which is a plane, there are 4 of them. In 3D space, we're going to get 8 rectangular prisms. So 1 here, 2, 3, 4 on the bottom, and then another 4 up on the top. So what I'm doing in this slide is looking at each, I'm not sure how to properly word this, but I'm going to be looking at each rectangular prism. There are 8 of them. I'm going to be looking at each of them independently. So this is the origin. So if this is the origin, this is coming out of the blackboard. That would be positive X. This is going up. That's positive Z. This is coming to the right, so it would be positive Y. Now let's take a look. If the origin is here, now this axis is heading into the blackboard. That makes it negative X. This is going straight up, so it's positive Z. This is going to the right, so it's positive Y. Now that we're over here on this corner, that's the origin. This axis is coming out from the board, so it's positive X. This is going straight up, it's positive Z, but this one's now going to the left, so it will be negative Y. So negative Y, positive X, positive Z. Looking at this particular one here, that is going back into the blackboard, so that is negative X. This is heading to the left, so it's negative Y. That's coming straight down, so it's negative Z. Now let's look at this one here. And again, I forgot to mention, but feel free to pause so you can think about this on your own. All right, the origin is here now. This is coming out from the blackboard, positive X. This is heading to the right, that's positive Y. This is heading down, that's negative Z. So positive X, positive Y, negative Z. This particular one here, what's happening here? Heading into the blackboard, negative X. Heading to the right, positive Y. Heading down, negative Z. So negative X, negative Z, positive Y. All right, next one. We are having our origin back here. And so what's happening now? This is positive X because it's coming out of the blackboard. This is heading to the left, so that will be negative Y. This is heading down, so it's negative Z. So positive X, negative Y, negative Z. And one last place we could position the origin. So imagine if you have a Kleenex box in front of you, you have 8 vertices. Each one of those vertices could be the origin, and then each version of that is representing one of those 8 rectangular prisms that would make up 3D space. So here we are here. We are heading backwards into the blackboard. That is negative X. We are heading up, so that is positive Z. We are heading to the left, so that is negative Y. All right, so hopefully you're able to wrap your head around this. It does require some bit of spatial thinking. All right, points and vectors in R3. All All right, so we saw what R2 looked like. In R3, not surprisingly, we need 3 coordinates, one for the X, one for the Y, one for the Z. So this point is going to be located from our origin, which is right there, 0, 0, 0. We are going to come A units in the direction of the X-axis, B units along the Y-axis, and C units along the Z. The position vector, OP, which I've drawn right now, will now have its tail at the origin and its tip at A, B, C, and we're going to write it this way. This is how we denote the vector. That's a Cartesian or an algebraic form, and it turns out we're not going to be able to give a geometric form for a vector in R3. It would require 3 different angles. We only need 1 angle to define a vector in R2 geometrically. We would need 3 in R3. And imagine if you extended this to R4 and Rn and so on. So when you move beyond R2, what you're going to see is vectors are going to be represented algebraically. And as I've already mentioned, A is the X component, B is the Y component, and C is the Z component. Right, so what we're going to do now is we've created this rectangular prism, and every vector can be surrounded by a rectangular prism. If you have a box of Kleenex, imagine connecting from one corner to the diagonally opposite corner. That would be your vector, and the Kleenex box being the rectangular prism surrounding it. So what we're going to do now is think about what are the coordinates of each of these points. So if we think about this, here is A right here, and what's happened is we have moved along the X-axis, but we have not moved along the Y or the Z. So the X coordinate will be A, and the Y and Z coordinate are both going to be 0. So let's take a look at that. Now let's look at point B. So what's happened? We've moved along the X-axis. We have also moved along the Y-axis, but we have not moved along the Z-axis. So we should be A, B, 0. Now let's look at point C, which is over here. So what's happened on point C? We've moved along the Y-axis. We have not moved along the X, nor have we moved up along the Z. So the coordinates of this point should be it should be 0, B, 0. Let's find point D. It's up here. So for point D, we've now moved along the Y-axis, and we've also moved along the Z-axis. We have not moved along the X-axis, though, because that would require us to move this way. So the Z component is going to be 0, the Y component B, and the Z component C. Point E, what's happened here is we've only moved along the Z-axis. So the X and Y component remains 0, the Z component becomes C. So 0, 0, C. Point F, we have moved along the Z-axis and the X-axis. We've moved along the X-axis and the Z-axis. We have not moved on the Y-axis, so the Y component is 0, the X component A, and the Y component C. All right, so the next thing you might be asked to do. All right, so what we're looking at here are some examples. So we've covered the definitions of what is the definition of an algebraic vector, what does it look like in R2, what does it look like in R3. You might be asked to plot a vector in R3. So the first thing I would like you to do is plot the point 8, 6, 4, and then illustrate it with a rectangular prism. So the first thing we're going to do is show where the origin is. It's right there. And then I need to plot 8, 0, 0. So 8, 0, 0, I'd come out in this direction all the way out to 8. There's 8, 0, 0. Now 0, 6, 0 would be, don't move in the X direction, move in the Y. 1, 2, 3, 4, 5, 6. 0, 0, 4 is only move in the Z direction, so 1, 2, 3, 4. That would be that one right there. 8, 6, 0 would be, well, let's go 8 in this direction. 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6 in the Y direction. That's going to be that point right there. 8, 0, 4 would be come out 8 this way and then go up 1, 2, 3, 4. We're not moving in the Y direction. That would be that one. The point 0, 6, 4, well, we've moved 6 to the right, and now we're going to go up 4. That's going to be that point right there. And now this next one would be a bit trickier. So if this were a test question, I would definitely give you a grid that looks like this so you can be accurate. Now we're going to have difficulty. How are we going to position this one correctly? So what I'm going to suggest you do is, we can see this line, is I'm going to suggest you hold a ruler. So let's just say this is my ruler, like that. And then I'm going to hold my, whoops. So that's parallel to that. So I'm going to slide my ruler up so that it passes through there. And then I would need a second ruler, like that, that I'm going to hold vertical. And then I'm going to pass that through here. And where those two intersect, again, so I got to hold a ruler parallel to the x-axis, and I'm going to hold a ruler parallel to the z-axis. And then that is exactly where that point's going to be. So that would be my recommendation for you on a test. Make sure you have two rulers. One that you can hold horizontal and one that you can hold vertical. Let's delete that. Delete that. And that was our point 86, 4. To show the rectangular prism, you just draw all of the line segments. So I'm just going to show you that. There's the rectangular prism connecting the points. Now the vector is going to connect the origin to this point here, and it's going to look like that. And we can't get a feel for perspective here, so maybe what I'll do at some point is pause so that I can show you in some 3D modeling what that vector would look like. And there's our vertex labels. All right, so just to give you a better perspective, I'm using the GeoGebra. It's a 3D calculator. Now in GeoGebra, this is the x-axis, this is the y-axis, so it's not the orientation that we're used to. So I'm just going to try and turn this a little bit. So that looks more like what we're used to seeing. So I can't put it that way. So I'm going to do it more like this, right? All right, so this would be the x-axis. There's the y-axis, there's the vector. Now I'm going to spin this around just to give you perspective. So there we were in GSP. We're having a hard time getting a perspective on how big that vector is. And our y-axis is horizontal and our z-axis is vertical. It's going to be difficult for me to duplicate that in here because when I try to do that, unless I do it, can I do it like that and come tip down? It's difficult because you can't see a delineation between the two. So, kind of drop it there so you can see. Now, I'm going to spin this around so you can get a perspective. So when you look here, you get a better perspective on, where that vector is in R3. Very difficult when you're looking at, so our 2D rendering was, something like this. It looked like a very tiny vector, right? Can't tell how big that vector is. Wonder if I can come over here and hide that. No, I cannot. New to this calculator, so I'm not sure how to hide things. Those dots are really big. So you see you get a better perspective by spinning this around. In fact, that vector is quite larger than the space we're seeing there between 8, 6, and 4. So there are some, when we put it right here, it looks like it's a very short vector, and when we come over there, we can see. So the problem we have now in doing this in Geometry Sketchpad is I'm losing perspective, but you can move to a 3D calculator to get better perspective. All right, example number 2. Point P is located in R3, so that its coordinates are -4, 7, -5. What I would like you to do is tell me what are the coordinates of A, B, C, D, E, and F. Now, let's be clear when we're doing this, that's the X component, that's the Y, and that's the Z. So if we're going to look at point A, what has changed? Only the Z component has changed for point A. The other two components should both be 0. So we're 0, 0, negative 5 because only the z component has changed. Point B, what's happening on point B? The z and the y component have changed, but the x component hasn't, because we have to move back into the blackboard for x to happen. So the x component is going to be 0, the y component is going to be 7, and the z component is going to be negative 5. Point C, what's happened here? We have moved only in the y direction, so the y component has changed. We have not moved in the z direction, nor have we moved in the x direction. So the y component will be 7, and the other two components will be 0. Point D is situated back here. So what's happened for point D is we have moved in the z direction, and we have moved in the x direction. Or we've moved in the x direction and the z direction. So the y component for point D should be 0. And the x component negative 4, the y component, or the z component negative 5 is taken from this ordered pair. Point E, what's happening on point E is we have only moved in the direction of the x-axis. So the x component will be negative 4, the other two components will be 0, because we have not moved in a z direction, nor have we moved in a y direction. And now point F is moving in both the x direction and the y direction. So the x component will be negative 4, the y component will be 7, but we have not moved down, so the z component will be 0. And then if you're going to draw a vector OP, then you would be joining this point to this point with a straight line. Show you that vector. And again, we don't have good perspective in this 2D rendering of this. If we want to get a better idea of what's happening, I suggest you go to a 3D calculator. And now it wants us to think about the plane that contains A, B, D, and P. So that would be the plane here. So what's true about this plane? What's constant? Well, let's think about this. I am moving in the x direction, and I am moving in the y direction on this plane. What I am not doing on this plane is moving in the z direction. So the z component must be fixed on that plane. This plane is in fact parallel to the xy plane, which would be up here, defined by those two. So it should look like all points of the form x, y, negative 5. And we can also say that z is equal to negative 5. The other way to write that, I had just noted, would be the points that look like this, x, y, negative 5. If I want to give it a Cartesian equation, it would need to be z equals negative 5. If we want to write a mathematical description of all of the points that are sitting in here, well, again, they would look like this, x, y, negative 5. But I would now have to say x is constrained between 0 and negative 4, and y is constrained between 0 and 7. So x, y, negative 5, so that negative 4 is less than or equal to x and less than 0, and 0 is less than y, which is less than 7. Next example. So on this slide, we've got geometric vectors here in blue. And then we've got all of these algebraic vectors in green. And so what you would be doing is, which vectors are most similar and which are most different, however you want to word that. These are definitely vectors in R2. These are vectors in R2. These vectors are in R3. These vectors are having sort of similar points. I guess if we look over here, we can see some vectors that have the same magnitude, right? Those vectors have the same magnitude. So those are looking at some similarities and differences. What I would like you to do is group vectors which are the same. So what is the best way to do this? You might want to change these to algebraic form by doing r cos theta, r cos 45 for the x component, r sine 45 for the y component, or else you can take the Cartesian form, and once you have the Cartesian form, you're going to have to say theta is the inverse tangent of the y component over the x, or you can say that r is the square root of x squared plus y squared. So that would be my advice. Either convert these 6, sorry, there's 6 of them, convert those 6 to geometric using Maybe I'll jump you back here so we can see where that was. It was here. So if you're going to go from Cartesian to geometric, theta is the inverse tan of y over x, and r is the square root of x squared plus y squared. Maybe it's easier to just go from geometric to Cartesian because we're just going to use r cos and r sine theta. So after you've done those conversions, you can see how they would match up. What I'm going to do is I'm just going to move to the next slide, and I'm going to show you what the correct answers are. I'm not going to show you what the work was. If we were in class, usually what I do is I give everybody a card that has a vector on it, and I tell them, now you need to go find who you are the same as, and again, using the formulas I showed you on the previous slide. So these two vectors are the same. 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 And these two vectors are the same. Now, these vectors are different. So I mentioned earlier, vectors in R3 can't have a geometric form because we can't define the direction with a single angle. You'll see in the next unit we could give direction angles with respect to each axis. But it's very difficult to describe an R3 vector using a single angle. All right, that brings us to the end of Lesson 5, and Lesson 5 is looking at Cartesian or algebraic forms of vectors in both R2 and R3. The next lesson we will continue, we'll be looking at properties and operations of vectors in Cartesian form. If you've made it to the end of this lesson, thank you for watching. Don't forget to stay tuned for Lesson 6. And as always, take care.